Hello everyone, welcome to week 5 of the course Introduction to Rings and Fields, NOC 24 MA29. I am PMRFTA Pawan Kumar Raikwade. So I will be explaining some sample problems here which will help you understand the concept better and solve the assignments, your weekly assignments. Okay, so let's start. Okay, yeah, hello. Yeah, am I audible? Hello, am I audible?
Sir. Yes, audible.
Okay, thank you. Okay, so let's recall. In last session, we had seen what an Euclidean domain and what a principal ideal domain is. Let me see if the recording is working. Yeah. So we call. So what we have seen is an integral domain E is called a Euclidean domain if there exists a norm n on E such that for any A and B belongs to E, there exists some Q and R belongs to E such that you can kind of divide with B. BQ plus R with n of R is either 0 or let's know R is 0 or n of R is strictly less than n of B. Okay? So kind of you have Euclidean division, something like Euclidean division with respect to this norm n. So if there exists such a thing, then you call the integral domain E as Euclidean domain. Right? And what we have seen is in an Euclidean domain, every ideal is principal. Right? So the point we have seen is in a Euclidean domain, every ideal is principal. Right? Example, you can say any field is Euclidean domain, and if you consider ring uh, Z over X is not a Euclidean domain. Why? Because ideal generated by 2 and X is not principal. Okay. So also this property that any ideal is principal has its own big importance. Why? Because these ideals which possesses this property are called as principal ideal domains. So there's another definition we have, PID. What is this? Uh, if every ideal is principal. So naturally, every ED implies PID, right? Because we already saw that in a Euclidean domain, every ideal is principal, hence by definition it's a PID. So now what are the important properties that are covered in these two major classes of integral domains, ED and PID? So that we will see further. So now I'll introduce some definitions. That R be an integral domain one. So I'll define first what a prime element is. First definition is of prime element. So an element P belongs to R is called prime if for any A and B belongs to R, P divides AB will imply P divides A or P divides B. This is like the property of prime numbers in set of all natural numbers, right? If a prime number divides product of two numbers, then it divides at least one of those. Right? So if you go in ring theory, the division is of course defined naturally, like we say A divides B if there exists an element C such that B equals to AC. Okay, this is the natural definition of division. So with this definition, any element P is called prime if it divides product, implies it divides either of those. And then there's a second definition called reducible element. So there are two ways to define this. Either I'll define reducible element or I'll define irreducible element. I'll define irreducible element. It's better. Okay, an element R is called irreducible. R which is non-zero and non-unit. So any non-zero and non-unit element R is called irreducible if whenever you write R as AB with A comma B belongs to R, then either A is a unit or B is a unit. That is, basically no non-unit element can divide R. Again, in integers or natural numbers, you can see only prime numbers possess this property, right? Other than prime, you can always write any composite number as a product of two non-units, right? Their units are just 1 and minus 1. So this is the definition of irreducible elements. And similarly, associates are just multiples by units. Okay. We'll define the third definition. Associates. So two elements A comma B belongs to R are called associate in R if there exists a unit U in R such that A equals to BU. They just multiplied by a unit. That's all. Those are the associates. Okay. So what is the relation between these prime elements, irreducible elements, and associates? So first relation we observe, proposition is that in an integral domain, prime elements are always irreducible. A prime element is always irreducible. Let's prove this. So suppose this prime element is prime, and you write P as let's say AB. I would show either A and or B are uh, units. Okay. So since P equals to AB, that means P divides A. I mean P divides AB, right? But which implies, okay, this is not implies, that is P divides AB, but which implies P divides A or P divides B, right? So if P divides A, then you can write A as some P times C, right? But this will imply P equals to P times CB. But you are in integral domain, right? So there is a cancellation. It implies 1 equals to CB. But what this says, right? This means B is a unit, right? Because you have a multiplicative inverse, right? There exists a non-zero element C such that BC is 1, right? So if P divides A, then B is a unit. And similarly, if P divides, if P divides B, then what do you get? Then you get B equals to some P times, let's say C dash. And then you can write P equals to A, P C dash. And by associativity again, 1 equals to A C dash. I mean commutativity, sorry. So this will imply C dash, I mean A is a unit, right? So in any case, either of those will be a unit, right? This shows that P is irreducible. So whenever you write P equals to AB, this will imply P is irreducible. I mean either of those is a unit, right? Okay, is this clear?
Yes.
No, thank you. Okay, so what we have seen is in an integral domain, every prime element is irreducible. So what about the converse? Right? Is it true that every irreducible element is prime? Yeah.
Not
So
always true.
not always true. Yes. So do you have any counter example?
Not remember, not right now.
Okay, okay, yeah, but okay, it's not always true that any irreducible element is prime. So let's before that let's give one proposition about prime elements. It's a very easy observation. So for any integral, okay, let I be an integral domain. So P belongs to I is prime if and only if ideal generated by P is prime. This follows basically by definition. So keep this in mind. We'll use this, that an element is prime if and only if the ideal generated by the element is prime ideal. Right. Now look at the next proposition. Okay, or I'll just name this as 1 and then this as 2. P belongs to I is irreducible. So the question is the similar works ideal generated by P is maximal. So is this if and only if? So this is generally not if and only if. Only one direction is true generally. So if element, sorry, the other direction. If the ideal is maximal, then that element is irreducible. Okay? This is generally true, but the other way around is not true. Okay, so we'll prove this. See, if this works, let's say if the other way around is also true, if the converse is also true, suppose this holds, then uh, then what do you get? So okay. Hmm. Right, I'm writing other direction. If this way holds, then you take any prime elements. Let P belongs to I is irreducible. Sorry, you take any irreducible element, then this direction will imply ideal generated by P is maximal, and we know every maximal ideal is prime, but then one will imply P is prime. But so what do we get? Every irreducible element is prime, but this is not generally true, right? Hence, yeah. So this is a quick proof that the converse does not hold. So this converse is not generally true. Okay, I mean, this converse. So now we'll prove the original direction. So one is very easy. I'll just give a quick proof. Uh, Prime. So claim is ideal generated by P is prime ideal, right? Suppose element A belongs to or not, for prime we take product, right? AB belongs to ideal generated by P. What this implies, AB equals to P times R, right? But this says P divides AB, right? This is just meaning of P divides AB. But since P is a prime element, we get P divides A or P divides B. But in that case, your element A belongs to ideal generated by P or B belongs to ideal generated by P. Okay. So this shows that every prime element, for every prime element, the ideal generated by the prime element is a prime ideal. What about the converse? That ideal generated by P is prime. Now let P divides AB. Right? What this implies? This implies AB belongs to ideal generated by P. Right? But since ideal is prime, this implies either A belongs to generated by P or B belongs to ideal generated by P. But this will implies P divides A or P divides B. Right? So it's a very um, quick and easy proof that an ideal is prime if and only if the generator is prime. I will go for the second proof. Second proof, we have to show that the ideal generated by P is maximal implies the element is irreducible. So that ideal generated by P is maximal. Okay, this is given. Now that I want to show that element is irreducible, right? So consider the factorization P equals to AB, where A comma B belongs to R. Or I took I, no, integral I. So how do I show that either A is unit or B is unit? Okay. So suppose, so what does it mean? If P equals to AB, then this will imply P belongs to ideal generated by A, right? Right? And this will imply ideal generated by P is contained in ideal generated by A. Right? But since my ideal is maximal, this will imply either this or this. Right? Since it is maximal ideal. But when does an ideal generated by an element is the whole ring I, if and only if the element is unit, right? This will imply A is a unit, right? And in this case, you can write A as P times some R, right? Because A will belongs to ideal generated by P. So this implies P equals to PRB, which implies 1 equals to R times B, which implies B is a unit, right? So if you start with ideal generated by P is maximal and you consider any factorization B equals to AB, then you end up either A is unit or B is unit. This is precisely the definition of irreducible element. Right? So this will imply P is irreducible. So naturally we ask the question that which are the rings where the converse is true, right? So irreducible if and only if prime, something like this. Okay. So we will prove the principal ideal domains are such important class of integral domains. Theorem: in a PID, that is principal ideal domain, a non-zero element is prime if and only if irreducible. So this is the significance of principal ideal domain, that every basically a prime element is always irreducible, we know. So in a PID you get the converse also, that every irreducible element is prime. Right? Now one side is already showed, that PI uh, that P belongs to I, prime P prime implies P irreducible is already shown. Now suppose P is irreducible. So if my element is irreducible, I have to show it is prime, right? So if I show that the ideal generated by P is maximal, then naturally it is prime ideal. Then directly it will imply that P is prime element, right? But we have already shown that an element is prime if and only if the ideal is prime. So what we will try to show is the ideal generated by P is maximal ideal. So our claim will be ideal generated by P is maximal. Proof goes similar way. Let take another ideal generated by P is contained in J. J be an ideal. So, so don't confuse. I is not an ideal. I is the ring. Okay, the integral domain that I took originally. Okay. Did I define anywhere? Okay. If not, I'll just start with R. Okay, not R. R be my integral PID. So now since R is the PID, there exists an element, let's say Q, so that J is ideal generated by Q, right? Every ideal is principal. That's what principal ideal domain means. So this implies ideal generated by P is contained in ideal generated by Q. This implies P is equals to some Q times R, right? Because P belongs to ideal generated by Q. Now we'll use that P is irreducible. Right? Since P is irreducible, one of these two has to be unit, right? So either Q is unit or R is unit. Okay. What happens in both of the cases? If Q is unit, this implies ideal generated by Q is the whole ring R. Hence we are done. And if R is unit, then you can write uh, Q as P R inverse, right? From here you just multiply by R inverse left side, then you get Q equals to P R inverse, which implies ideal generated by Q is, see, right now we just get Q belongs to ideal generated by P, but this naturally will imply this. So what do you get? You already have this P is contained in Q, then you have ideal generated by P is same as ideal generated by Q. So this is what the definition for maximal ideal is, right? You take any ideal J which contains this ideal, then either that ideal is the whole ring R or the ideal is same as ideal you started with, right? So this will imply ideal generated by P is maximal, right? And since every maximal ideal is prime, we get is prime. Hence by above theorem, I mean the theorem we just discussed, P is prime. Right? So what do we get? Every prime element, every irreducible element is prime, right? So I mean, in the proof of this, what we have shown is P in PID maximal if and only if P is irreducible. So if we analyze a bit further about maximal ideals and prime ideals, so what do we get? Right? I know that an element is irreducible if and only if prime. Now I have just shown. But then I know an element is prime if and only if, sorry. So, okay, so I should change this. Hmm. Okay, how do we phrase? Yeah, so from here I get, yeah, this is right originally. So P reducible implies P prime, but this will imply ideal is prime. Right? So we get something more that we already got, by the way, in last some propositions, that in a PID every prime ideal is maximal. Right? Generally, in a commutative ring, in an integral domain, what we have is every maximal ideal is prime, but you don't have the converse. But in a PID, you have the converse also. Every prime ideal is maximal. Okay. So you have any doubt?
No, sir.
Okay. Okay. So we'll go further. Okay. So now there's next concept is unique factorization domain. So sir has defined already in the lectures UFD. It is unique factorization domain. So what this means is any element has a factorization which is unique up to associates. Right? It is I an integral domain for any P belongs to I. There exist irreducible elements, let's say Q1, Q2, QR, such that P is equals to Q1, Q2. You can factorize also if P is equals to, let's say, for any R L star or for any A L star. A is equals to, let's say, P1, P2 up to Pn, then you have n equals to R and Pi equals to some Ui times Qi, where Ui are unit. Right? So basically you have the factorization, and the factorization is unique up to associates. Right? So the detailed description is given in the lecture videos you can watch. So what is the point that I want to point it out right now is there was a proposition I mentioned that if or let R be the integral domain in which factorization terminates, then R is UFD if and only if you have the following: every prime element is every irreducible element is prime. It became very congested, but I hope you can see. So you have an integral domain in which factorization terminates. And what do you have? That integral domain is UFD if and only if every irreducible element is prime. Okay, this is a very important proposition because now we can directly uh, judge which of the very famous integral domains are UFD or not. So, as you already know that in Noetherian rings, factorization terminates. Noetherian means every ideal is finitely generated. In particular, all principal ideal domains are Noetherian rings. Factorization terminates. Hence, you have the following proposition. every PID is UFD. How to prove this? See, you know that every PID is Noetherian, and factorization for any factorization for any element terminates. Now, if you observe this proposition, what do you know? If in an integral domain factorization terminates, then it is a UFD if and only if every irreducible element is prime. But we have just shown that in a principal ideal domain, right, every irreducible element is prime, right? We have just shown here. In a PID, every irreducible element is prime, non-zero, of course. Hence, by what do I call this? Let's say this is proposition 2, and this is proposition 1. Then by 1 and 2, we get the required result. Okay, so what we have shown that every principal ideal domain is UFD, yeah, unique factorization. In particular, every Euclidean domain is UFD. Right? So these are very bigger classes of integral domains which are naturally there everywhere, and you know now that they are all UFD, unique factorization domain. So this is about UFDs and PIDs. So these are very general integral domains. So now we will start some field theory. Just give me a minute. Okay, so I will start some field theory. So what is a field? So it is by definition it has to be an integral domain such that every non-zero element has unit. Basically, for any non-zero element, you have a multiplicative inverse. That's the definition. So, I'll give one proposition, which is also an example. Every finite integral domain is a field. Okay, so let's prove. So how to show that? So let I. So because it is finite, I will just label the elements a1, a2 up to, let's say, a n be an integral domain. Now I'll define a map phi from I to I. I mean, take any element I. I mean, let's say I'll take a1 or any element ai. And now how I define the map? Phi for any element aj, basically ai times aj. And this is the product defined already. Now since I is an integral domain, we get phi is injective map. Why so? Because if, let's say, phi of some aj a l is same as phi of some am, this will imply ai times al is same as ai times am, right? But what do you get? You get ai times al minus am 0. Now you are in integral domain, hence al equals to am, but this will implies phi is injective. Now you have a map from a finite set to finite set which is injective. This will imply the map is also surjective, right? For a finite set, injectivity is same as surjectivity. Surjective and injective called as bijective, right? So what do you have? You have a bijective map phi from I to I, right? Now you have an integral domain. There exists one. One is the element belongs to range phi, right? This implies there exists some aj such that phi of aj, which is ai times aj, is 1. That's all. No? Then this will imply ai is a unit. Of course, you started with a non-zero element, otherwise you don't have a injective map, right? So what I have shown is that in a finite integral domain, any uh, any non-zero element has a unit, right? So every finite integral domain is a field. Okay. Okay. So now the next thing is to define what is called a characteristic of a field. For any field f, the characteristic of a field is denoted by car of f. Okay, this is the notation for characteristic field, and is defined as it defined to be the smallest positive integer p such that p times identity of f is 0. Now what this times means, this is simply adding one p times. Okay, this is simply 1 this is identity of f plus 1 plus p times. Okay, so if you add 1 p times and then you get 0, then the field is of characteristic p, and if such a p exists, and if does not exist, then you define 0. If p such a p does not exist, then you define car of f to be 0. Okay, so what are the examples? Examples. Suppose you take f to be your real numbers. Okay, now tell me, if I add in your real numbers identity is 1 only, right? So if I add 1 or like any finitely many times, okay, any, let's say p times, then do I get 0? No, right? Naturally, I mean, this is absurd. Adding some
No,
1 to real numbers and expecting 0. So there cannot exist such a p for which p times 1 is 0. Right? This is the definition of p times 1. This implies characteristic of R is 0, which is also characteristic of your complex numbers, also characteristic of rationals, right? So these are like infinite fields basically. These are infinite fields which are characteristic 0. Now what about finite fields? What do you expect to be the number p? So that is always prime number. Okay. So what follows is the proposition. The characteristic of a field f is either 0 or a prime number. Okay. So, so for infinite fields, you know it is 0. So suppose the characteristic of f is not 0. Suppose there exists a number n, I mean p only I called, such that p times f is 0. Right? Now suppose if p can be written as ab, that is p is not prime, right? Then what do you get? You get p times 1, like adding an element ab times is same as adding an element a times, then multiplying with and adding element with not element 1 basically 1 b times, right? This is 0. So there are two elements in your ring, right? Integral domain. So when is the product 0? Product 0 only if some of one of the elements are 0, right? So you have either this is 0 or, right? But then this is contradiction, right? So what I started with, finite. So what do you mean characteristic is p? P is the smallest, right? That is p is the smallest um, number such that p times, I mean when you add 1 p times you get 0. This is such a smallest number is called as characteristic. But now you are getting a number which is smaller than p, yeah? Because p equals to a times b, such that a or b times f 1f is 0. This is not possible. Hence p has to be prime, because contradiction happened because I assumed p as a composite number, right? So characteristic of any finite field is prime. Okay. 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 So now let's Okay, so you know, right? Z quotient PZ is prime. Z quotient PZ is field, right? ZP is field basically, right? So let's don't use any algebraic tools we have and they use whatever notions we have developed till now and prove that ZP is a field. Okay, so see, Z quotient PZ is basically what Z one ideal generator of P, right? And you know this is field if and only if this is maximal, right? So what are the maximal ideals if and only if P is irreducible, right? We have shown before, right? In a PID, right? In a PID, we have shown that every ideal is maximal if and only if the generator is prime, right? Sorry, generator is irreducible. But what this means, that is, if P equals to AB implies A is equals to plus minus 1 or B equals to plus minus 1, right? Because those are the only units in your integer Z. So this implies what? P is a prime number. So P is reducible if and only if P is a prime number. That's all, right? That means what I have proved is ZP is a field if and only if P is prime. Right? So it's the basic applications of the ED, PID, and irreducible prime elements. Right? So now, no, so now what will be the characteristic of this field? It will be P. Now we will analyze on a very important homomorphism. So see, what we were doing right now, we are doing multiplication, right? We were defining for any n times 1f is adding, right? N times. So we also define minus n. So like this doesn't make sense, no, adding it minus n times. But what we define is minus of n times 1f basically. This will give you an element and then take the negative of it, right? And 0 times 1f is basically 0 you define. This to with these two convention, now you define a map phi from integers to your field f as phi of any integer n is n times the identity. Right? Now this is a well defined map because you have already defined what it means for positive, negative, and 0. Okay? So this is a well defined map. Easy to show that is a homomorphism. So now since phi is a homomorphism, right? What do you know? What do you have? What is kernel now? See, kernel phi is set of all integers n such that equals to 0, right? But what you will get here? So like that means it's a multiple of characteristic basically. Right? But then this you have a nice notion. This is char f z, right? So like how you represent pz or nz. This is characteristic of f is an integer, right? It's a natural number, so you define it in this way. Right? So let me check if recording is fine. So everything is well defined here. So kernel phi is well defined. Kernel phi is characteristic of f times z. So what you have is uh, yeah. So range of phi is isomorphic to z divided by kernel phi, right? So what are the possible choices for kernel phi, right? So what you know is kernel phi is, because characteristic can only be 0. If it is 0 z, then it is basically z only, right? I mean, not 0 z, sorry. If it is 0 z, then it is singleton 0. And if it is p, then it is pz, where p is prime. These are the only choices for kernel. Then range of phi is either isomorphic to z by singleton 0, which is basically z, or z by pz, right? So what is the conclusion? If so, I mean, any field, for any field has the range phi will be a subring, right? And now you can see this is a field, right? And if a field has z, then naturally it has q, right? Because you have any integer, you divide all the integers, and then you can form rational numbers, right? So any field has either a subfield isomorphic to q because coming from integers, or zp coming from here, right? So this is a very important result, that any field you give, it has a subfield isomorphic to rationals or ZP. That's all. Okay. So it has a subfield isomorphic to rationals if its characteristic is 0. It has a subfield isomorphic to ZP if its characteristic is prime P. So I hope everything is audible.
Yes, sir.
Just give me a minute. If internet connection is unstable, I'll do something. Yeah. Okay. Yeah. Okay. So now there are concepts of field extensions. Okay. So, see, if you consider an equation x square plus 1 belongs to r over x, right? So, this is polynomial which doesn't have any roots in r, right? But on the other hand, you see r is contained in c, right? Complex numbers. And x square plus 1 has the roots in c, right? So, this is a very important observation. Like, what so we have to reach there, right? What we want to find ultimately is for any field, let's say f, and you given a polynomial px in fx, we want to find a superior field k such that the field k has all the roots for this polynomial px. Okay, so such a field is called a field extension. I mean, not such a field. Any field containing a root field is called as field extension. Okay, now I'll define what a field extension is. if K is a field containing the subfield F, then K is said to be an extension field of F and denoted by, so this is a weird notation, this is not set subtraction or anything else, this is just denoting like this. You have K is a superfield of F, in some sense. Okay, and now there's another definition. Whenever you have a subfield, if K is a uh, if K is an extension of F, or in other words, I'll write suppose. Yeah, so this means K is an extension of F. Then K forms a vector space over F. Right, it forms a vector space. So since it is a vector space, you ask for the dimensions, right? So definition is, you have a box symbol of K colon F, is this is the number, is dimension of vector space K over field F. Okay, so I mean if it is finite, otherwise you say infinite, that's all. Example, you take F to be R and K to be C, right? Then you know that C is a field extension of R. So set of all complex numbers forms a vector space under the field R. And what do you have K F? This is 2, right? So dimensions of complex numbers with real field is 2. Yeah, this is surprising. Dimensions of field complex numbers with itself is 1, but if you take the field as real, then it's 2. Dimension is 2. Okay, and if I take, let's say F is Q and K to be R, right? So real numbers are naturally extensions of rationals, right? It's a field, it contains rationals. So do you get this is finite? This is the question. So is this finite?
Not final.
Huh? I cannot hear you. Yeah, so it cannot be finite. Why? Because see, any finite dimensional vector space is isomorphic to Fn, where F is the field, okay, subfield under which it is taken. So if it's finite, then F, okay, or I mean real numbers would be isomorphic to, I mean basically this is F, K is isomorphic to F raised to this number, okay, that is here R would be isomorphic to rational raised to whatever the degree is, I mean whatever the dimension is, let's say n, where n is, right, if it is finite. But is it true? No, right, because here you have the tuples a1, 8, I mean, yeah, a1, because rational is countable, and if you take the finite product of rationals, it is again countable, right? It's countable, and R is not countable. Hence, this is not isomorphic. Hence, this is not finite. Kf cannot be finite. I mean, okay, this is true, and this is infinite. Okay, you cannot write that like this as a symbol, but you can say that the dimensions of real vector space considered over the field rationals is infinite. Okay? This is about the field extensions. So, yeah, you have any doubts?
No, sir.
Okay, if not, then we'll stop today. I have, yeah, this won't be a 2 hour session today. Okay. If you have any doubt, you can ask. Okay. We'll continue next week, Monday. Thank you.